Hello, everyone. Welcome back to Markov processes. I guess I'm just going to pick up where we left off. We were talking about the period of a state of a Markov chain. So we were motivated by the random walk, a simple random walk where we were on integers. And at each point in time, you could go up one with some probability p or down one with some probability 1 minus p. You couldn't stay flat and you couldn't go up more than one at a time or go down more than one at a time. So we were looking at state 0 in particular. And if you leave state 0, you can return, well, you can't return in one step, but you can return in 2. You can't return in 3 steps, but you can return in 4. In fact, you can only return in 2, 4, 6, 8, 10, 12, etc. You can only return in an even number of steps. And the greatest common divisor of all of those numbers is 2. So we say that state 0 has period 2. And there was nothing really special about state 0. The same thing could be said of state 5 in that random walk. And we actually don't even have to think about that state separately because we proved at the end last time that periodicity is a class property. So if you have two states, I and j, and they communicate, if I has some period, say 5, then j must have period 5. And if we have one giant class, let me share my screen here. If we have one giant class for the Markov chain, in other words, it's irreducible, and all states have period 1, we say that the Markov chain is aperiodic. An aperiodic Markov chain is a nice Markov chain. It means, well, when you add it to something like irreducibility, then you can move around the whole space, you can get anywhere from anywhere else, and you're not stuck in some sort of cycles where you can only get there in a certain number of steps. And it will be nice if we could come back to states. So if we had positive recurrence, and in fact, all of these things, positive recurrence, irreducibility, and aperiodicity are going to be sufficient conditions for us to get some pretty nice results. Now, remember what we were talking about a couple of classes ago before we went into classification of states and recurrence and transience and all that. We were talking about the limiting distribution of a Markov chain. I have a theorem for you, and it's going to be one of a group of important theorems that I am going to label not like 1, 2, and 3, but I'm going to label this theorem pi 1 for reasons that should become apparent in a few minutes. So theorem pi 1 goes like this. For an irreducible, positive recurrent, aperiodic Markov chain, and we are still talking discrete state space and discrete time, the limit as n goes to infinity of the probability of going from I to j in n steps exists and does not depend on that starting value I. I'm tempted to say is independent of I, but I don't want you to think of random variables, but that would be an appropriate word as well. So what does this sort of mean in a picture? I'm going to have a state space axis and a time axis. And I'm going to start a Markov chain in some state I, and I am going to run it forward. So I think the easiest way to think about this is in simulation. So I'm going to, at time 1, I'm going to grab a uniform associated with time 1, a uniform 0, 1 random variable. And I'm going to look at the ith row of the transition matrix and all those probabilities in there. And I'm going to see if the uniform is less than the first probability, then that will tell me what state to go to. Otherwise, if it's greater than the first probability, but less than the sum of the first two probabilities, that will tell me where to go. And we will run forward. And again, and again, and again for a very long time. And by a very long time, I mean an infinite amount of time. And wherever we end up at the end is going to be kind of a simulated value from the limiting distribution, which clearly you can't get to in real simulations. or can you? You just wait. So if I were to start from I again, I would end up somewhere else potentially. I could end up at the same point again. I might end up somewhere else. Maybe I come back to this point, and eventually, if I collect all the output, there's going to be some kind of distribution associated with the output. And the shape of this distribution is the limiting distribution that we've been talking about. And it's not supposed to depend on where you start, because the chain has run for so long, it can't remember where it started. So assuming this limit exists, we're going to give it a name. And first, let me just rewrite the limit here as n goes to infinity of Pij. This name should not depend on I, because this quantity doesn't depend on I. And it's going to actually be a probability. So we might call this like P sub j, but there's just way too many P's floating around, and this probability is way too special. So we're going to call it pi, being the Greek letter for P sub j. And this is not just my preference. This is a pretty universal notation for the limiting probability. The probability you are in state J down here at the end of this infinitely long run Markov chain. I think I just said that pi j is a probability, and let's just make sure of that. So note that because I left off my n. So because the Pij super n is a probability, it's between 0 and 1, and the limit is between 0 and 1. So that means that pi j is between 0 and 1. And if we sum over all j in the state space, our pi j, then that's going to be the sum over all j in the state space of the limit as n goes to infinity of Pij super n. And if we interchange the limit and the sum, then I'm going to have the limit and then the sum as j runs over S of Pij super n. So this sum is running over the entire ith row of the n-step transition matrix. So we're starting at state I, and we can either go to, I don't know what the states are. Just because it's discrete doesn't mean it's integers, but let's say the state space is 1, 2, 3, 4 on up. So we can go from I to 1 in n steps with some probability, and from I to 2 in n steps with some probability, and I to 3 in n steps with some probability, etc. And we have to go somewhere, even if it's just back to I. So those probabilities add up to 1. This is summing across the ith row of a transition matrix, an n-step transition matrix. So this is the limit as n goes to infinity of, sorry about that, of 1, which is 1. So what we've just seen is that if you sum over all the pi j's, you get 1, and the pi j's are between 0 and 1. So they are, in fact, forming a probability distribution. Okay, let me just write that down. They form a probability distribution on the state space of the Markov chain, which we usually call S. So I'm just going to write on S. And we usually collect these in like a row vector. So in the example that S is only the states 1, 2, and 3, we might talk about pi as the entire distribution as the collection in a row vector of pi 1, pi 2, pi 3. And we may put a vector on this pi or not. We may just talk about the distribution pi. Okay, I have another definition for you. A distribution pi. Now, this is not necessarily a limiting distribution. So why am I calling it pi? Bear with me. On a state space S for a Markov chain is a stationary distribution for the Markov chain if the following equation holds, which is known as the stationary equation. I'm just going to write it first, and then we'll talk about interpreting it. So if pi j is equal to the sum over all I in the state space of pi I Pij. What does this mean? The word stationary, means something that is not changing in time. And if you imagine this through simulation, now the stationary distribution is a very theoretical quantity, and you might never think about it in terms of simulation, but I think simulation really helps make these ideas a little more concrete. So here I have a time axis and the state space and time 0. And I am going to start not from an arbitrary I that I just pulled out of the air, but an I that I pulled from this distribution. So we have some pi is going to have some kind of shape. And for this picture, I mean, I don't know what the bin widths are, but let's say pi can have 4 possible values. And I grab a starting value, which is most likely going to be in here, less likely going to be out here, but it's going to be somewhere. And so let's just say for this example that it's right here. So that is a quote unquote draw from pi, a simulated value. Pi is some, in this case, finite discrete distribution. So you can imagine it tabulated and grabbing a uniform and breaking up the interval between 0 and 1 into the different probabilities and seeing where the uniform falls. So after you get this draw from pi, if you look forward to time 1 and you grab another uniform that's associated with time 1, so this has a uniform distribution on the interval from 0 to 1, then you can look at whatever this is. So if this is a state I, then you can look at the ith row of your transition matrix, and you've got the probabilities of moving to all the other states, and you can compare your uniform with those probabilities and figure out where to go. And so maybe your chain goes here. And if I started all over with a new draw, an independent draw from the stationary distribution, and maybe that one comes out here, and went forward with a new uniform as well, then I would end up somewhere like maybe here. I don't know. And if I did this over and over and over again, they would build up into a shape which is actually the same shape as the one we started from. This distribution is stationary in that it's not changing in time. And you can see that from this equation. What we're doing is like the probability we're in some state J, we can get it by looking at all states I, the probability that will be in a state I over all the states, and then the probability that we move from I to J. So this is like your initial draw from pi, this is a movement, and this is just running over all possible starting states. So this is a stationary equation or distribution for a Markov chain. So what if we went forward another time step? I'm going to make this time step extra wide just because I don't have enough room to draw. So time 2 is out here. If we kept following our first path, which was here, forward, it might go here. And maybe this other path goes here. And we run a whole bunch of paths. What are we going to see when we run a whole bunch of paths? If we collect the output, we should see the same distribution, because if you start with a draw from this distribution, then move forward one time step, you get another draw from this distribution. So now at time 1, I am just starting with a draw from the distribution pi and moving forward one time step. It's very Markovian of us. We're starting all over again. So if I start with a draw from pi, I end with a draw from pi. And so now you can think of this as a draw from pi that you're going to start with to move you somewhere else. So you're going to keep seeing that distribution over and over and over again. It's stationary. It's not changing in time. And therefore, we can say that pi j is the sum over I in S of pi I p ij super n. This is another stationary equation. Now, if you want to prove this, I would prove this by induction on n. So let me move this down a little bit and say, suppose pi is a stationary distribution for a Markov chain with transition probabilities Pij. Then we have, by definition, that pi j is the sum over all I and s of pi I Pij. And I want to show that this implies this n-step transition probability stationary equation. So I'm going to use induction. I'm going to do a proof by induction on n. So first you have to do it when n equals 1, but that's the given, right? This is the case where n equals 1. Then you assume it holds for a general n like this, and you want to take that and show that it will hold when you replace n with n plus 1. So I'm going to do that. I'm going to replace n with n plus 1 and start with that. Start with the right-hand side. I have the sum as I runs over s of pi I Pij n plus 1. Now I know the thing that's circled now holds, and I know that this holds. That's my assumption in this inductive step. So I am going to break up my Pij into 1 step and n steps. And I'm not sure which way I'm going to do this. I can do it either way. Like I can go, well, we're going to Chapman-Kolmogorov it. So this is the sum as I goes over s of pi I, and then the sum over some intermediate state k of, say, p I k, and then p kj in n steps. I could have put the n on the first p. That would work as well. So that is Chapman-Kolmogorov. And now I'm going to interchange the orders of the sums. And so I get the sum over k, the sum over I of pi I Pik, and then the Pkj super n. And then by stationarity, I know that this is pi sub k. So let's go back up here to the original stationary equation. If, I ended in j and this corresponded to pi sub j, and now I'm ending in k. So this is pi sub k. And that means that I have the sum over k of pi k p kj super n, which is in this circle up here, which was assumed as part of our inductive steps, assumed to hold. And that means that this thing is going to give me pi sub j. So I get pi sub j, but you'll notice I started with the n plus 1 in there and got down to pi sub j. So that's the final step of induction. We have shown that this n-step stationary equation holds. If you're seeing a vector and maybe a column of a matrix, then you're not seeing things. That's really there. The stationary equation, the original one, so pi j is the sum over all I and s of pi I Pij. This is running across a row vector of pi's and down a column in the P matrix, the transition matrix. What you're seeing, this thing is the jth entry of the vector matrix equation. The vector pi is equal to the vector pi times the matrix P. If you're less comfortable with matrices and vectors, I mean, you can completely get away from them in this course, but you don't have to use this equation. You could stick to the individual equation for each j, and you'll get through the course just fine. But yes, I know you see it over here. It appears that pi is a left eigenvector of the probability transition matrix, and it corresponds to an eigenvalue of 1. Our transition matrix has its rows summing to 1, and even if it it's not a matrix for transitions of a Markov chain. If you have a matrix filled with probabilities whose rows sum to 1, it's called a stochastic matrix in general, even if it's not a transition matrix. And we can show, and we might show this depending on how much time we have, that any stochastic matrix has an eigenvalue of 1, and then all the other eigenvalues are in magnitude less than or equal to 1. And so here we have the case where we have an eigenvector with an eigenvalue of 1. And a cool thing that happens here is the second largest eigenvalue actually controls the rate of convergence to the limiting distribution pi. Oh, but this is not a limiting distribution here, it's stationary. So why did I bring stationarity up when we were talking about limiting distributions? And why did I use the same notation? It turns out most of the time, these are going to be one and the same. So the next thing I want to prove to you is this claim that a limiting distribution is always stationary. I am going to define, so I'm going to prove this right now. I'm going to define pi j as the limit as n goes to infinity of pij in n steps. And I want to show that this is stationary, which means I want to show that the stationary equation pi j equals the sum over I of pi I pij. I want to show that that holds when I define pi j with this limit. Yeah, so I'm going to start with the right-hand side of this. I'm going to write out the sum over all I in S of pi I, pij. Now my pi has been defined by this, but it's pi I. So the I is in place of this j. So I do need the I over here and not over here. And the I from this equation is really arbitrary. I can start anywhere. So I'm going to start at like a state k. In other words, I'm going to write the sum over all I and s of the limit as n approaches infinity of p k I super n p I j. And then I'm going to interchange the limit and the sum. And we've got a Chapman-Kolmogorov equation staring right at us. So this particular sum combines and takes you from state k all the way to j in n plus 1 steps. So this is the limit as n goes to infinity of p k j in n plus 1 steps. But if you take the limit as n gets large, n is still getting large even if you add 1 to it. So as n goes to infinity, this limit is the same as this limit is pi j. So I get equals pi j. And if you look at the left-hand side that we started with to the right-hand side, we started with pi j defined through a limit, and we showed that it is stationary. All right, so a limit, if it exists, and we have a theorem, our pi1 theorem, that gives us some sufficient conditions for existence of the limit, is always stationary. You might not have a limit, and you could still have a stationary distribution. You might have a limit which is stationary and have a non-unique stationary distribution, so you'll have another one that is stationary that's not a limit. And so we have a lot of cases to consider. Let me write these down in a couple of notes. Number 1, stationary distributions may not be unique. And as I was saying, you might have multiple stationary distributions, one of them corresponding to a limit, one not, or maybe there's no limit at all, but somehow you have 3 stationary distributions. For most well-behaved chains, the limit exists and the stationary distribution is unique. And if that's the case, they are one and the same. So we have more pi theorems coming where we're going to try to get a handle on all of these cases. But right now I'd like to do some computation because we've been in a more theoretical side for a while. So I think we can use a little computational break. So right now I want you to assume that the limit exists and the stationary distribution is unique. Since the limit is stationary, that means there's not another stationary distribution. So the limiting distribution and the stationary distribution are one and the same. Maybe that looks weird because I use plurals there, distributions and limits, when there's a unique one, but I'm talking about in all the different examples that are about to come up. So for my first trick, I'd like to go back to homework 1. I believe it was problem 1. And in that problem, we had a couple of boxes and we had 8 balls, some of which were green and some of which were white. We had a total of 3 green balls and 5 white balls. And we labeled the boxes 1 and 2. And the balls are distributed in such a way that there are 4 in each box. So as one example, suppose I have 2 green here and 2 white. Then I have 1 green here and 3 white. And we let xn be the number of green balls in urn or box 1. I guess I said box and now I'm on to urns at time n. And although there's up to 4 balls in urn 1, there can never be 4 green balls in there because there aren't 4 green balls in the system. So the state space here, the values that xn can take on are 0, 1, 2, and 3. And we found a probability transition matrix in our last homework assignment. And I don't want to take the time to rederive this, so I'm just going to tell you what these are. Across the top row, I get 1/4 and 3/4, and then a couple of zeros. Across the next row, I get 1/8, 1/2, and 3/8, and then 0. The next row, I get 0, 3/8, 1/2, 1/8, and in the final row, I get 0, 0, 3/4, 1/4. So I have a question for you, and that question is, what is the long run proportion of time there are no green balls in urn 1 or box 1? I can't make up my mind on that. So the number of green balls is given by the Markov chain. And so we want to find a limiting distribution, and we want to find the probability we're at state 0 in the limit. So the answer, the thing we want to compute, we want what we're calling pi 0. And because we're assuming that the stationary distribution for the chain is unique, if there is a limiting distribution, it is the stationary distribution and they are one and the same, then we can use the stationary equations to find this long run probability or long run proportion of time as I've written it. So the stationary equation is pi j is the sum over all I and s of pi I pij. And so if we try j equals 0, we have pi 0 equals, and then we get a sum as I goes from 0 to 1 to 2 to 3. So we get pi 0 p00 plus pi 1 p10 plus pi 2 p20 plus pi 3 p30. And what we've done to get an equation for pi 0 is we've gone through all of the pi's in order, and we've multiplied them by these coefficients running down the 0 row. And once you realize that, you don't have to think so hard about this equation. You can just grab the coefficients by running down the columns. So give me a second to copy and paste this matrix. Okay, the equation for pi 0. I'm going to run down the 0 column of the matrix. And these are coefficients for pi 0, pi 1, pi 2, and pi 3. So I get 1/4 pi 0 plus 1/8 pi 1 plus 0 times pi 2, which you do not have to write, but for our first system of equations, I want to make sure you can see where all the coefficients came from, plus 0 times pi 3. To get an equation for pi 1, I'm going to go down the 1 row of the matrix, and I'm going to use these as coefficients for pi 0, pi 1, pi 2, and pi 3 respectively. So I've got 3/4 pi 0 plus 1/2 pi 1 plus 3/8 pi 2 plus 0 pi 3. And again, I don't need to write the 0 term. And then I'm going to run down the 2 row. So pi 2 is 0 times pi 1 plus 3/8 times pi 2 is 0 times pi 0 plus 3/8 times pi 1 plus, so I'm going down this column, 1/2 pi 2 plus 3/4 pi 3. And finally, going down the column labeled 3, the fourth column, I have 0 times pi 0 plus 0 times pi 1 plus 1/8 pi 2 plus 1/4 pi 3. So I have a system of equations that hopefully we can solve for pi 0 in. And because they're all entangled, we're going to have to solve for all of them and then pick out pi 0. But you'll notice that, why did I grab for the highlighter? You'll notice that there's a pi in every single term. So if I have a solution given by the vector pi 0, pi 1, pi 2, and pi 3, and I multiply that vector by 8, that's still a solution, because that would put an 8 in front of this, and this, and this, and this, and this. So an 8 could factor out of the right-hand side and cancel with the left-hand side. So there are an infinite number of solutions here. So we need a constraint, because hopefully we're not going to have numbers multiplied by 8. These pi's are supposed to be probabilities. Our constraint is going to be pi 0 plus pi 1 plus pi 2 plus pi 3 equals 1. And now the system is overdetermined. There's 4 unknowns and 5 equations. So what you can do is take all but one of these. So leave one out and put this in and solve that. I am just going to grab the first 3 equations to take with me to the next slide. And the constraint, pi 0 plus pi 1 plus pi 2 plus pi 3 equals 1. And you can solve this any way you want. If you want to do a lot of back substitution, you might do that. I think it's easiest to turn this into a matrix vector equation. So that's what I'm going to do. I'm going to have some coefficients in here, and I'm going to multiply by the column vector, pi 0, pi 1, pi 2, pi 3. And then I'm just going to write out these equations. So like the last equation, we'll have coefficients 1, 1, 1, and 1, and it's supposed to equal 1. For the other equations, I'm going to choose to move everything to the left-hand side. I'm going to subtract some stuff over, which means that I get pi 0 minus 1/4 pi 0. So I get 3/4 in here that's going to be multiplied by pi 0. And when I move the 1/8 pi 1 to the left-hand side, I have negative 1/8, and the others are 0. So moving to the next row, I'm going to move this 3/4 pi 0 to the left-hand side, and that's going to be negative 3/4. And then I'm going to move this 1/2 pi 1 and subtract it from this 1 pi 1. So I have a positive 1/2 pi 1. And moving this over, I'll get negative 3/8 and a 0. And I didn't leave myself a whole lot of room. Let me just move these ones down a little bit. Okay, so going into the third row, I have 0 pi 0. I'm going to have negative 3/8 pi 1 when I move things to the left. You can move things to the right. You can do this completely differently. You just need to solve this somehow. I'm going to have positive 1/2 pi 2 when I take this and subtract it to the other side, and negative 3/4. By the way, for your homework, you are allowed to use Mathematica, MATLAB, whatever you want, a symbolic manipulator, or you can do this with decimals and just, not have something that can do the symbolic manipulation. You're welcome to use any software, any kind of calculator you want, and then to get through your homework. But when we have exams in here, you're not going to have to solve big systems of equations. The questions will probably say like set up the system, but do not solve, or potentially maybe solve a tiny 2-variable system with 2 equations. So yeah, don't worry about having to solve this in real time on an exam, but hopefully you can figure out ways to get it done for your homework. So when I move things to the left in these first 3 equations, there's nothing left on the right, which means I have 0, 0, 0 over here. And so if I want to get the pi vector, I'm going to need to multiply by the inverse of the matrix, and I will get, here's the pi vector, and this is equal to this matrix inverted times the vector 0, 0, 0, 1. So I'm not inverting this live. I took care of this. I hope I got the right thing. What I saw was, so this gives me pi 0 equals 1/14. Pi 1 is 3/7. Pi 2 is 3/7. And pi 3 is 1/14. And what we wanted was pi 0. So the long run proportion of times that there are 0 green balls in box 1 or urn 1 is 1/14. Let's do another example. I have an airport / hotel shuttle driver, or shuttle. I don't care about the driver. And it moves between the airport, and I'm going to call the airport A, and 2 hotels that I'm just going to call B and C. And I meant to write this all out as a long word problem so that we can pull out the right probabilities, but I'm feeling lazy. So I'm going to go straight to the transition matrix. So if you're wondering where I'm getting these numbers from, I am making them up as my example. What I would have said if I wrote out the words was, assuming the shuttle is at the airport, it's not going to just go back to the airport. So it's not going to go back to where it is directly in any case. So I'm going to put zeros on the diagonal. In other words, if it's at A, it's got to move away from A. If it's at B, it has to move away from B, etc. And let's say the 2 hotels are equally likely when you're moving from the airport. So let's say if we're starting at Hotel B, we're going to go back to the airport with a very high probability, but occasionally Hotel B is overbooked or something, and people have to move to Hotel C. So I'm going to make this like 9/10 and 1/10. And just to mix it up, I'm going to go from Hotel C to the airport with probability 8/10 and 2/10. So here is my question. What is the long run proportion of time the driver or the shuttle is at a hotel? The hotel could be B or C, and the shuttle can't be at both at the same time. So being at B and being at C are disjoint events. And this means our answer, we want to get those long run probabilities, pi A, pi B, pi C, and our answer is going to be pi B plus pi C. So let's get our system of equations. Just going to try to write it here and drag it down. For pi a, I'm going to run down the a column and I'll get 0 pi a. This is the last time I'll write the 0 coefficients. I just really want you to see where every number is going. Plus 9/10 pi b plus 8/10 pi c. And then going down the b column, I have pi b is 1/2 pi a plus 0 pi b plus 2/10 pi c. And I'm going to write the third one down just for the record, but we're not going to use it because we need to bring in the constraint that these sum to 1. And that means we need to kind of ditch one of the equations. But pi c is going to be 1/2 pi a plus 1/10 pi b plus 0 pi c. And we need the constraint that pi a plus pi b plus pi c is 1. And now 3 variables and 4 equations is overdetermined. I'm going to use these first 2 equations. You might pick any 2 and you might look at them and say, oh, this one has a lot of zeros in it, so I prefer this one. But for lack of a better idea, I'm just going to grab the first 2 equations and the final equation, and I'm going to set this up. You could do back substitution, but I'm going to do just what I did before. So the top equation, let me get the vector in here, pi a, pi b, pi c. If I move everything to the left-hand side of the top equation, it appears that I have 1 pi a, negative 9/10 pi b, and negative 8/10 pi c. If I go to the second equation, I have negative 1/2 pi a, 1 pi b, and negative 2/10 pi c. And then if I go to the constraint, I have 1, 1, 1. And in the upper equations where I moved everything to the left side, there was nothing left. So I have 0, 0. And then for this final equation, I have a 1 on the right-hand side. So pi a, pi b, pi c is going to be this matrix inverted and then multiplied by the vector 0, 0, 1. Now, when I did that, I got pi a as 98 over 213. I was really into using fractions when I can. I mean, why not have total accuracy? But you certainly don't need to do this. And I would also probably want to convert these to decimals anyway to get a sense of the percentages here. But yeah, I get pi a is 98 over 213, pi b is 20 over 71, and pi c is 55 over 213. And so remember, the answer we're looking for is pi b plus pi c. So that's 20 over 71 plus 55 over 213, which is equal to whatever it is. You could stop there on an exam or even on a homework. I don't really care about simplification. I care more that you understand the Markov stuff, although you might be curious as to what the long-run proportion of time actually is, so you can follow through to the end. So I want to do one more example of a stationary distribution, and at this point you might think this is getting repetitive, kind of is, but there's a specific reason I want to look at this example. So I have a troll who lives in a cave with 2 entrances or exits, one on the north side and one on the south side. So this troll is going to go grocery shopping, and the troll has 4 canvas bags. And let's say every time he leaves his cave, he's going grocery shopping. Or let's just say he's not even going grocery shopping, but every time he leaves his cave, he wants to take 1 canvas bag with him. So he needs one bag every time he leaves the cave. And he piles them up by the door, much like I do when I come in the house. I just drop everything by the door. The door that he comes home to. These are pretty bad sentences. So he is equally likely to depart and return from either door completely independently. So where he departs does not dictate where he returns or anything like that. So equally likely to use the north and south, and I guess they're not doors, entrances for departure and arrivals. And these are independent choices, independent of everything else. So again, if he leaves from the south door, he may come back to the north door or the south door with probability 1/2. It doesn't matter that he left from whatever door I just said. So he needs one bag every time he leaves the cave. And so he's going to grab one if it's there. But occasionally all the bags will be piled up at the other door and he's departing from a different door. So in that case, he will have no bag. He's too lazy to go to the other door. And so he grabs one bag if there are any. From the departure, let's just say this cave has doors on it. I keep saying doors. The departure hole in the wall, the departure door when he leaves the cave. And he always needs one, but sometimes he has 0. So what we want to find is what is the long run proportion of time he goes with no bag. So we're going to set up a Markov chain, and there are a couple ways to do this. It's going to be really hard if you try to consider which door he's leaving from. I kind of don't care. He's leaving from some door, and the Markov chain is going to be like, if there's currently 3 bags at the departure door, be it north or south, how many bags are there going to be at the next departure door? So I'm going to let xn be the number of bags at the nth departure door. Again, I don't really care whether he's departing from the north or the south. And the state space is there could be 0 bags there, or 1 or 2 or 3 or 4. So let's work out the matrix. Okay, so he's got a couple of doors. They're not doors, whatever, entrances. And he's departing from a door where there are 0 bags. And I don't care which one of these is north, one of these is south, but let's say this is the departure door and then this is the other door. So the situation is 0, 4. He leaves with no bag, which means he doesn't move anything. When he comes back from the grocery store, he doesn't put any bags back because he didn't take anything with him. So the next day's departure, since he is equally likely to depart from the 0 door or the 4 door, we get, starting with 0, the next day, he'll start either with 0 with probability 1/2 or 4 with probability 1/2, and the others will be 0. So that one is one of the easier ones. Let's try to do the 1 row. So he is departing from a door that has 1 bag. So again, I'm going to call this the departure door. It's not north or south, it's whatever he's departing from. And this means that the other 3 bags are at the other door. So when he returns with the bag, he could come back to the same door that he departed from and there will be 1 and 3 again. Or he can come back to the opposite door. So he picked up this one bag and left, and he came back to the other door, leaving 0 here and having 4 here. So these are the 4 options for departing the next day. And they're all equally likely. So we get 1/4 on 0, 1/4 on 1, 1/4 on 3, and 1/4 on 4. So let me try to explain that just a little bit differently. He's departing from the door with 1 bag. So I don't have to consider that probability. That's already fixed and given. How will there be 0 bags at the next day departure door? 2 things have to happen. One thing is, since he left here, he needs to bring the bag back here in order for there to be a 0. And he will come back here with probability 1/2. And then the next day, he will choose to leave from the 0 door with probability 1/2. So we get 1/2 times 1/2, and that's how we're getting this 1/4. Okay, the next state to consider is 2 bags at the departure door. And that means there's 2 bags at the other door. And so if he takes a bag from here and returns it to here, the next day, there will be 2 and 2 when he departs. Again, I know this is weird. This is not a north and south door. This is like the door he departs from and the other door. So if he's leaving from this door, this is our departure door, and he takes 1 bag and he returns it to this door, then the next day there's going to be 1 here and 3 here. And so you can see that there are 4 outcomes, but 2 of them are the same. There's 2 2s, and all of these outcomes are equally likely. And that means that this gets probability 1/4, this gets probability 1/4, and 2 gets 2 probabilities 1/4, adding up to 1/2. So the 2 row of the matrix, we can't go to state 0. We can go to 1 with probability 1/4. We can go to 2 with probability 1/2. We can go to 3 with probability 1/4, and we can't go to 4. And if you wanted to write that out, you would say he's leaving from door 2, and the way that he can have 2 bags from his next departure door is that he, number 1, has to return to the original door so that there's 2 and 2 there, and that will happen with probability 1/2. And then the next day he can leave from either door. So he's going to leave from either door with probability 1. So this comes from 1/2 times 1. Okay, so now I'm just going to kind of fill out the rest just to, in the interest of time here. The 3 row is going to be 0, 1/4, 1/2, 1/4, 0. And the 4 row, you might think it's going to be the same as the 0 row. It's not, and I'll tell you why, but it's 1/4, 1/4, 0, 1/4, 1/4. If this was a bigger matrix, like if he had 20 canvas bags, you'd really see the pattern of this diagonal and below the diagonal coming in and then coming out like an X, but it's hard to see with this small matrix. So you might be wondering why the 4 row was not symmetric with the 1 row, sorry, the 0 row. So you might be wondering why the 4 row is not symmetric with the 0 row. And the thing is, if he leaves where there are 0 bags, then he moves nothing. And the next day, he can either go from the 0 bag door or the 4 bag door. And that will be probability 1/2 each. But if he leaves from the door with 4 bags, he may not return it there, and he can actually change the situation to 3 and 1 for the next day. So it's different because this is saying he doesn't take any bag with him on one of his departures. And this is saying he does take a bag. So things are moving before his next departure. And that's why the 0 and 4 rows are not the same. So we want to find the stationary distribution here, and we want pi 0 because remember, we were asked for the long run proportion of times he leaves with 0 bags. And we can do this problem just like we did all the others. We can set up the pi equations by running down the columns. But the reason I wanted to do this third example was something interesting is happening here. If you look at each column, the columns are summing to 1, which is not something that you usually have with a probability transition matrix. And when the columns sum to 1, we say that the matrix is doubly stochastic. It doesn't happen all that often, but when it does, the stationary distribution is very easy to find. So the stationary equation, you'll recall, is pi j equals the sum over I and s of pi I pij. And what we normally have is if we sum over the ith row of the transition matrix, we get 1. But if you look at just the sum as I goes over S of Pij, what that's doing is summing down the jth column. And every column here sums to 1 in this doubly stochastic case. So if this wasn't here, this right-hand side would be 1. What if I put a constant in here and a constant over here? Then the constant will come out of the sum and we'll get C equals C times 1, which holds. So a constant works, a constant probability for all states 0, 1, 2, 3, and 4. Because that's 5 states and these have to add up to 1, that means that pi 0 is the same as pi 1, is the same as pi 2, is the same as pi 3, is the same as pi 4, and they all have to be 1/5. And assuming there's only one stationary distribution, we're done. And in fact, I can tell you there is only one here. We're eventually going to get to the theorems that tell us when to expect a unique stationary distribution. But isn't that cool? For a doubly stochastic matrix, we can really solve the problem without going through all of the linear algebra we had to do for the other problems. It's pretty slick. Okay, so it looks like we are out of time. When we come back, we're going to hit theorem pi 2. Oh, by the way, we didn't prove theorem pi 1. These pi theorems take a long time to prove, and I want to prove at least one, if not more. But I can't prove every one because each one will take at least an entire lecture. So I've decided that pi 2 is a more interesting proof than pi 1, which is why I left theorem pi 1 without a proof. But you can check it out in the notes if you have the stomach for it. It's kind of hard. But next time I'll state theorem pi 2 and prove it, and that one is not going to be about a limiting distribution, but about existence and uniqueness of a stationary distribution. Next time on Markov processes.